Okay, so to derive Stirling's formula, what we want to do first is to think of factorial n as a continuous function of n, right? We know that for n is actually an integer, right? So this, if I think of it as f of n, this is not a continuous function of n. But for large n, we want to, it's convenient to think of it as a continuous function. So how do we do this? So I want to introduce an idea here, and the idea is that of analytic continuation. Have you guys heard of analytic continuation before?
No, sir.
Not really.
Okay, so this is a very important concept that comes from complex analysis. And the idea is something like this. Suppose you have a function, and the function is in general a complex function, and it's defined on some domain, say U. So this is U, and the function is defined here, f of U. And the thing about this function is that, so let's call this, say, complex plane Z. So this is the real part of Z, and this is the imaginary part of Z, okay? So you can think of Z as X, and imaginary of Z as Y, and then this Z as X plus IY. So now we also assume that f is this function f of Z in this domain, which is defined in the U domain. It's an analytic function. So this is an analytic or holomorphic function. How many of you haven't had complex analysis?
I haven't.
I didn't.
Okay, so this is, you don't need a lot, but in complex analysis, a special place is, there's a special place in complex analysis for functions which are analytic or holomorphic. And what these functions do is that they satisfy a particular equation which is known as the Koshi Riemann equation, okay? And the Koshi Riemann equation, when expressed in terms of complex variable Z, can be expressed in this way, that it's the derivative of f of Z with respect to f of Z bar is 0, right? When expressed in terms of the complex variable Z, it's almost a triviality. So this is the Koshi Riemann equation. Okay, so once you have that, then there is a theorem, or there is a very well-developed theory which tells you that such a function can be extended to all of the complex plane, patch by patch. So there is another, say, area like this which overlaps with this. So you can find a function here, say called G, such that G of Z, let me change the color, G of Z is equal to f of Z when they are, let's call this, patch V, when U n in the intersection of U and V, okay? So in the n, G of Z is also analytic. So G of Z is analytic in V, and this is analytic in U. So there is a unique function. So in a sense, G of Z is the extension of the original function to a bigger ungraded domain. And you can think of both of them as the same function. That kind of makes sense, right? So what we are going to do is that we can think of factorial n as a function which is only defined on the integer points, positive integer points of the complex plane. So you can think of Zn as a complex variable. And so far, it's only defined, this function is only defined at these points. And then what we are going to do is that we are going to find an expression for n that coincides with this function at these points, but it's also analytic in other points. And therefore, this function can be thought of as an analytic extension of factorial n. And this function, you can verify, is this function, factorial n, can be thought of as 0, an integral from 0 to infinity, x to the power n, e to the power minus x of dx. Okay, so when you do, when you do math physics or mathematical methods or some other class like that, you will see that this is called the gamma function. But this is, so first of all, what you want to do is that you want to verify that the claim I made here is true, that if that this function is actually factorial n at these points, right? Is it obvious from this?
Not quite, sir.
Yeah, it's not obvious to me either, right? So, so let's do it for one by one for everything. So we'll have to. This class is going to be Hilbert's class, so we will be here for forever. Do you guys know about Hilbert's Hotel, by the way?
Yes.
The Infinite Hotel?
Yes. So we are going to prove this factorial n for all n, right? So it's like
by induction, I suppose.
Yes, exactly. We're going to do it by induction. Okay, good. So let's just do it first for 0. So factorial of 0 we know should be 1. So so this is going to be 0 to infinity, e to the power minus x, d of x. And if you do the integral, we get minus e to the power minus infinity plus e to the power 0, which we know is 1. Okay? And then you can do integration by parts, and you can generalize this to so you can show that if this is true for, say, n, factorial n, if this formula is true for factorial n, then this formula is true for factorial n plus 1. Do you want me to show that?
Yes.
No, sir.
One said no, did somebody say yes?
Yes, sir.
Okay. If somebody wants to, even if a single person says yes, I'm obliged to show it. Okay, so I will show it, even if you are. So sorry for those who are going to be bored, but first of all, we are going to use integration by parts formula. So do you all know the integration by parts formula?
Yes, sir.
Yes, sir.
Okay. So so let me just write it down because I actually have to derive it all the time. So I always forget. And it's something like this, right? If we have two functions of x, then we have the integral of one and the other one. And there's and then minus, you take the derivative of the other one and you integrate that, right? Something like this. Okay? So if you do this, then let's start with, say, factorial n. So this is 0 infinity x to the power n e to the power minus x of dx. So then what we do is that we just factor one factor of x apart. We just peel it apart, and we have xn minus 1 e to the power minus x times x d of x. And then what we want to do is that, we want to integrate this guy. When we integrate this guy, we get x squared by 2. And then the other factor just goes on for a right, xn minus 1 e to the power minus x. And the limit here is infinity and 0. And minus, inside the integral, we have to differentiate this factor now. So this factor is d by dx, x to the power n minus 1, e to the power minus x, and this factor is x squared by 2, d of x. And then, so here, from the first guy, we see that e to the power minus infinity is 0. And then we have x 0. So the first thing just gives me 0. And here, the second term, by the Leibniz rule, we get two terms here, right? One of the term is 0 to infinity. And then we have n minus 1. And then there's a factor of 2 coming from here. And then we have x to the power n minus 2, but there's a factor of 2 here, so there'll be x to the power n, e to the power minus x, d of x. And then we have this guy acting on this will bring me a minus sign, so we will have a plus here, and then 0 to infinity, and then x to the power n plus 1 divided by 2, e to the power minus of x, d of x, right? And now, if we look at this guy, we know what this is. This is just this thing. So this is, so if you rearrange, we see that on the right-hand side, we have, again, the same thing here with this factor as extra. So if we take that to the other side, we get 1 plus n minus 1 divided by 2, 0 to infinity, x to the power n, e to the power minus x, d of x. And then this guy, which is, no, not this guy, which is half times x to the power n plus 1, e to the power minus x, d of x. And therefore, this is nothing but factorial n. And therefore, what we have done is that, and this is, if we simplify this just becomes n plus 1 times, and there's a by 2, and there's a 2, this 2 will cancel that 2, and we get n plus 1 factorial is 0 to infinity, x to the power n plus 1, e to the minus x, d of x, okay? So then what you do is that you basically do an asymptotic expansion of this when n is very large. And I will leave that as an exercise because I cannot do everything. So, and then you can derive the formula known as Stirling's formula. If you need help, you can look at Blundell. This is taken from Blundell. So, but I wanted to, introduce the idea of analytic continuation. So what we have done here is that we have taken the real line, the positive real line, and taken the positive integers and then expanded the function factorial n to all of the positive real line. But you can show that you can also expand this to the negative real line as well as the complex plane. So you can also go in that direction. Now, this function will have some singularities, and that's normal. Holomorphic functions can have singularities. Otherwise, it's actually not an interesting function. It just becomes constant. So, yeah, this is the idea I wanted to introduce is the idea of, the idea of analytic continuation. Okay. Okay, so I'm going to move on to probability distribution, but it's a good idea here to stop and ask for questions.